Yeah. Okay. Hi. Hello, all who've joined this meeting, both on YouTube and on Zoom, and for coming at 9:15. It's pretty early in the morning on a Saturday. Um, I'm Aditya. I'll be the host for today's event. Um, as you all know, this event that we're going to have today is a part of the Cosmic Zoom exhibition, and I'm assuming as you've joined here, you might already know about this exhibition. But for people who still don't know about it, I would just like to introduce the exhibition for you. So Cosmic Zoom is an interactive virtual exhibition because of the pandemic times. And it aims to showcase the concept of scale to the general public, scale right from the scale of the atom, the nucleus, to the scale of the cosmos, the very largest scales in our universe. Uh, you can check out all the material of the exhibition at the site called cosmic-zoom.in. I repeat, cosmic-zoom.in. And you can check out many fascinating videos, activities, and much more there. As a part of the exhibition, we also have a special lecture or a talk every day. And this also includes workshops and other things where one has the opportunity to interact with a researcher or a person, a science communicator in different fields. All the forthcoming events are listed on the website that I just mentioned, and of course, it's absolutely free. So please do log on to the site and register for any and all the events. With that out of the way, I would like to introduce our event for today. So we've all gathered here to for the screening and a conversation about Quantum Voyages. And Quantum Voyages is a theater piece created by Smita Vishweshwara, who's a professor of physics at the University of Illinois at Urbana-Champaign. She is very much closely connected to the scientific, educational, and cultural establishments in Bangalore. Her research spans the coldest states of matter in the universe and a lot of other wide variety of areas. And this is the the virtual edition of the stage theater play that you're going to see today is one of our efforts to bridge the boundaries between science and art, which she's been interested in for the past few years. So, Smita, may I invite you to speak a few words about the piece that we're just going to see? Thank you.
Thank you. A warm welcome to you all, and thank you for coming here on an early Saturday morning for you. For me, it's Friday night. So as Aditya said, what we'd like to do is to really take you into the quantum realm as an exploration, as a journey. And as Aditya mentioned, we'll be doing this through first screening this piece, Quantum Voyages, which Latrell Bright, a theater maker, and I collaborated on scripting. And it was really brought alive by a marvelous cast, crew, and also quantum sages, as we call them, real life physicists who come at key moments. So what you'll see is something that started off as live theater, but in the face of the pandemic, it was supposed to come to San Diego, where I am right now, though virtually I'm with you all in Bengaluru. And when the pandemic struck, there was the question on whether we go on creating the piece in whatever way possible. And the answer was yes, indeed. And so thanks to everybody joining in and saying that we'll do this, we now have the virtual production of this voyage into many a quantum realm. Enjoy.
Thanks, Mata. That was really nice introduction. And now we can start the screening of the play.
And should we also mention that if someone has questions on chat, if you
Yeah.
have any questions, so one advantage of this live screening is that you can ask questions on chat, and I'll try as best as I can to answer these questions.
Yeah, thanks. So please key in your questions in the chat if you have any during the course of the screening. Thanks. during the course of the screening. Thanks.
So Aditya is ready? We are ready.
Yes, please go ahead.
Yeah, thank you.
During the course of the screening. Thanks.
So Aditya is ready? We are ready.
Yes, please go ahead.
Yeah, thank you.
During the course of the screening. Thanks.
So Aditya is ready? We are ready.
Yes, please go ahead.
Yeah, thank you.
During the course of the screening. Thanks.
So Aditya is ready? We are ready.
Yes, please go ahead.
Yeah, thank you.
Tell us, O muse of those curious voyagers who traveled
during the
far
course of
and wide.
the screening.
Into
Thanks.
the depths
So
of the
Aditya is ready?
quantum world.
We are ready.
Many
Yes,
realms
please go
did they
ahead.
visit, of manners and customs unacquainted.
And time and again, they could not perceive the vastness.
The depth.
And so, guided they were by Sapienza, the spirit of wisdom, casting light upon these worlds.
But lo,
Though she could illuminate, only the discoverers could enlighten.
But who?
Tell
Who
us,
these
O
discoverers
muse
of those curious
sages,
voyagers who traveled
quantum
far
sages.
and
Real
wide.
life physicists
the
here on
depths
the
Aditya is ready?
quantum world.
We are ready.
Zoom.
and
Many
now,
Yes,
realms
please
did
go
they
ahead.
visit,
come
of
ye with
manners
us on
and
this
customs
quantum voyage.
unacquainted.
Accompanying our explorers, they could not perceive the vastness. And Akash.
The
The depth.
But hark!
And
The
so,
quantum
guided they
world
were
is
by
one most
Sapienza,
fragile.
the spirit
The
of
act
wisdom,
of observation
casting light
itself
upon
can
these
drastically
worlds.
alter its
But
substance.
lo,
And the manner in
Though
which
she
you
could
observe
illuminate,
can change its
only the
outcome.
discoverers could
So,
enlighten.
sojourners, we
Yeah.
invite
I
With
think
all
there
else
seems to be some
unraveling
problem with the
mysterious
stream.
worlds.
Immerse yourself into the quantum world that you are made
Yeah,
of.
it seems.
Observe with
Thanks.
an indulgent, loving eye.
And
just
just be
present
present
in
in
the
the
now.
now.
Nothing to be observed.
See?
Well, what do you mean, see?
What does it mean to see?
No, I mean, what do you see?
See?
I don't see anything. All of Tara's foo-foo stuff. What in the world?
We are light.
Radiation.
perhaps particles.
Perhaps waves.
Waves or particles, which is it?
Perhaps both.
But I don't see.
Depends on how you see.
But what does it mean to
What
see?
does it mean to see?
Whoa.
Whoa.
Do you see what I see?
I am Sapienza.
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 You are Tara and Akash.
Yeah.
How do you know our names?
Do you like to travel?
Yeah.
Yeah, how do you know our names?
Do you like to meet new people?
Yeah!
Like who?
Sages.
Sages. What are sages?
This travel of which you speak, I mean,
Are you adventurous?
will it be safe?
Will it be dangerous?
Light. The alluring elusive. The alpha and omega of creation. Light that poured out when existence came into being.
Oh, wow.
Okay, hey, Tara, I'm not so sure we should be taking trips with strangers.
When do we leave?
Oh, come on, Tara, can't we just take a nap? Oh, could be such a lovely nap. To sleep.
Oh, to awaken. Light. I like light. But really, what is light?
And the journey begins. Our first quantum sage, Professor Yizhuang Yu.
What's the nature of light? A puzzle that lasted for centuries. It dates back to ancient Greeks, when science has sprouted fertile. Pythagoras postulates that light is a steady stream of particles, while Aristotle considers light as tidal waves in the ocean. These two opposing ideas sow the hidden tension of war. Through the mist of Middle Ages came the age of discovery. The first wave-particle war broke out in the physics community. Both sides tried to explain the laws of reflection and refraction. They resulted in opposite predictions about the speed of light. However, light travels fast and its speed is hard to measure. Experiments at that time could not resolve the dispute. The war ceased for a century, waiting for new evidence to come. History enters a new era, the modern industrial age. Advances in technology led to new discoveries in science. Interference patterns appear as light passes through thin slits, and bright diffraction spots emerge in the darkness of shadows. These light spots are like tides in the sea that rise and fall. The particle theory can do nothing but suffer from defeat. The wave theory won gloriously the second wave-particle war. It declares light as a wave in the electromagnetic field. Peace has only been maintained for less than 20 years. The concept of light quantum resurrected the particle theory. The third wave-particle war had gone beyond the scope of light. The battle spread to all particles that had been discovered in nature. A peace treaty was finally made. Its name is called quantum. All matters are wave-particle dual. The same applies to light. Wave and particle live in peace under the quantum theory. Another century has passed. There should be no more war.
Sapienza,
Yes, Tara?
so does light travel fast?
Yes, Tara, faster than anything else.
Sapienza,
Yes, Akash?
are there miniature creatures like us in the quantum world?
No, Akash. The quantum world looks nothing like what you know, but you're composed of it.
Sapienza,
Sapienza,
Rest your minds. Light, the alluring elusive. Sometimes a wave, sometimes corpuscular bundles of energy. Sometimes here or there, sometimes here and there. The glue holding matter together. Light, the quintessential quantum. Quantum, it is the ancient world where curiosity leads to uncertainty. Light, the constant voyager, the messenger, peripatetic, bouncing, tunneling through, unstoppable, except in death, absorbed into being.
the photon has to die so that we can know of it and we can see?
It's not easy to see.
You have gotten a taste, and now I will take you to a feast of the strangest innards of quantum. To be or not to be, that is the question. Correction. To be and not to be. That is the, Man kann auch ganz burlesque Falle konstruieren. One can even set up ridiculous cases. Eine Katze wird in einer Stahlkammer gesperrt, zusammen mit folgender Hollenmaschine. A cat is penned up in a steel chamber along with the following device, die man gegen direkten Zugriff der Katze sichern muss, which must be secured against direct interference by the cat. In einem Geigerschen Seelord befindet sich eine winzige Menge radioaktiver Substanz. In a Geiger counter, there is a tiny bit of radioactive substance. So wenig, so small, dass im Lauf einer Stunde vielleicht eines von den Atomen zerfällt. That perhaps in the course of 1 hour, the atom decays. Ebenso wahrscheinlich aber auch keines. But also, with equal probability, perhaps none. Geschieht es, so spricht das Zählrohr an unbeteiligt über ein Relais ein Hammerchen, das ein Kürbchen mit Blattsäure zertrümmert. If it happens, the counter tube discharges and through a relay releases a hammer which shatters a small flask of hydrocyanic acid. Hat man dieses ganze System eine Stunde lang sich selbst überlassen, so wird man sich sagen, dass die Katze noch lebt. Wenn inzwischen kein Atom zerfallen ist, der erste Atomzerfall würde sie vergiftet haben. If one has left this entire system to itself for an hour, one would say the cat still lives if meanwhile no atom has decayed. Die Psi-Funktion des ganzen Systems würde das so zum Ausdruck bringen, dass in ihr die lebende und die tote Katze. The psi function of this entire system would express this by having in it both the living and the dead cat. A Spaufau, pardon the expression, zu gleichen Teilen gemischt oder verschmiert sind. Mixed or smeared out in equal parts. Die gegenwärtige Situation in der Quantenmechanik. The present situation in quantum mechanics, really.
Could you repeat that, please?
Welcher Teil mein klein Krummschnapper? Which part, my little crumb snatchers?
All of it.
All of it?
Let's try this instead.
You know how in that game, Clue?
Yeah, the one with that manila envelope?
Yeah, and all those murderers.
So, at the beginning, you don't know.
Yeah, you don't know who it is.
Anyone could be the culprit.
The possibilities are mixed.
Or smeared out in equal parts.
Yeah, I read that somewhere.
Quantum clue. At a birthday party, there is a tiny bit of evil, so small, and yet in the course of 1 hour, it bites one of the guests enough to commit the most heinous of acts. But also, with equal probability, any one of the other illustrious guests could have been bitten by this bug of evil.
Is this a fun party?
Shh. The consequence, the unfortunate and untimely demise of Dr. Geiger.
Round one. Classical clue.
Miss Scarlet in the bathroom with a wrench.
Colonel Mustard in the kitchen with the dagger.
Mrs. Peacock in the cellar with a revolver.
Mr. Green in the lavatory with a candlestick.
I gotcha!
Wait. Okay, wait. How did you know that?
Now, therein is the real question. The nature of reality.
What about me?
Perhaps until we observe it. All guests are probable fiends, except, of course, the poor, unfortunate Dr. Geiger. Every single guest, until the point of observation, carries the potentia of the bug of evil.
Round two.
Copenhagen clue.
Miss Scarlet in the study with a wrench.
Mrs. Peacock in the cellar with a revolver.
Mr. Green in the hall with a knife.
Colonel Mustard in the dining room with the lead pipe.
All possibilities are mixed or smeared out in equal parts.
Like in a game of musical chairs. Reality comes into being only when the game is observed and the music stops.
Ladies and gentlemen, I have followed a string of observations and concluded beyond a reasonable doubt that it is indeed Colonel Mustard who performed the heinous act in the dining room with a lead pipe.
So it's at this point that all the morbid possibilities, mixed or smeared out in equal parts, that we collapse onto Professor Plum being the true killer.
I beg to differ. I would like to think the killer existed all long before Detective Irwin's observations.
Oh, my little crumb snatchers. Reality, it could be way worse. All possibilities could be smeared out in equal parts, and that is the reality.
No way.
Yes way.
And so, we begin again.
Round three.
Multiverse clue.
Fine.
Colonel
This is
Mustard
what
in
you
the
do.
observatory with the revolver.
And so, they all exist at once. Nothing collapses. All possible scenarios are real, each in an actual universe of its own. In one, Mr. Green. In another, Mrs. Peacock. In another, Colonel Mustard. In another, Mrs. White. And perhaps, in yet another, Dr. Geiger sprains his foot and never shows up to the party, little knowing how fortunate they are.
That's efficient.
That makes my blood boil.
And Schrodinger's poor cat. What happened to her?
Same thing. In the first round, it is mixed or smeared out in equal possibility of being dead or alive until the detective opens the diabolical device and the state of the cat collapses into being either dead or alive upon observation.
And in the second round, in one universe, we could observe it being dead, and in another, equally real, being alive.
And in yet another, it could have tunneled out of the device altogether and disappeared. And that's only 2 rounds.
Well, which one describes reality?
Which one describes reality?
These rules may not be complete. We may be missing a whole other set.
What? So quantum mechanics isn't complete? Well, what is all of this for?
Oh, Detective Irwin should know.
Sorry, crumb snatchers. This is categorically beyond my jurisdiction.
Oh, please, we need to understand.
Oh, my little crumb snatchers, I'm afraid this is beyond my jurisdiction as well. But I know someone. Professor Kenan Trilligator. Oh, Professor!
The interpretation of quantum phenomena is indeed confusing. Copenhagen interpretation? Many worlds? A great physicist advocated the shut up and calculate interpretation. We know the rules to do precise calculations, which fit precisely with observation. But there's still something so mysterious and bizarre about it, even to the professionals. Roll the dice and see what possibility is realized. Is poor Schrodinger's cat in the box alive? Well, in some outcome, the answer was no. Maybe there's another world where the answer was yes. These look like two cats, but it's actually a single entangled cat. There's a certain magic to quantum mechanics, provided you don't look too closely. The observer just can't be detached. Spooky entanglement is everywhere. We could try to harness entanglement, maybe use it for quantum computing, but it's ethereal and easily broken. The collapse of the wave function, hidden variables, observation says no. It's just non-commuting observables and good old entanglement. And everything, even us, we're made up of ripples of quantum fields, a dynamical soup that fills space and time. Some fields can Bose condense, as happens with the Higgs field, or in a superconductor. Using the technology of materials and lasers, the magic of quantum mechanics is being illuminated and applied on larger and larger scales. But it's not yet scaled up to the level of the mysterious cat kit. Shut up and calculate. Remember the Bose-Einstein condensate.
Oh, the quantum worlds.
The nature of reality remains elusive, and yet
Quantumness is omnipresent,
germinating at the most minuscule realms,
where even the smallest of quantum particles are strong in character.
two breeds there are, the hostile fermions and the friendly bosons.
And if perchance fortune be favorable,
come they together in harmony.
these bosons in a manner most extraordinary,
forming a communal quantum state.
The Bose-Einstein condensate.
Bose-Einstein condensate.
Bose-Einstein condensate.
In the coldest spaces of the universe, when agitation from heat subsides and all quietens, a strange quantum state of matter can emerge, the Bose-Einstein condensate.
Where were these spaces?
Not far away in the cosmos, but right here on Earth. In pockets of near emptiness hover these quantum states, these condensates.
And what their composition?
Minuscule quantum specks, cooperative specks, colluding in concert, creating a common conglomerate.
Who the creators?
Why, humanity.
Us?
Us?
Why, yes. There are those who have unraveled the science and art of isolating atoms into the tiniest of spaces, cooling them to the lowest of temperatures, and bidding them to form the strangest states of matter.
Close encounters of the Bose-Einstein.
Hark! The tale of how the Bose-Einstein condensate comes to be. Oh, Smita, come ye! Professor Vishveshwara, do tell!
Here we are, my friends, at 300 degrees above absolute zero. Speaking of quantum condensates, not even outer space is cold enough for them, warmed to 3 degrees above zero by the cosmic light from the early universe. But back on Earth, cold atomic scientists, many my friends cast their wizardry on tabletops, enclosing a suspended gas of atoms in a glass case, sodium, potassium, or rubidium perhaps. Friendly atoms, bosons, which love to congregate, brought together to a clump by laser beams. Photons pelting, slowing, and cooling their motion. Yet, not cold enough until the invocation of an everyday trick, evaporation. Like with a cup of coffee, except in an invisible bowl formed of magnetic fields. The faster atoms flying out helter-skelter. The remaining slow, and cold enough, just a millionth of a degree above zero for a quantum magic transition to happen. For each atom to fill space as a wave, each wave to overlap with the other, indistinguishable, together to act as one, move in harmony, free of friction, free of rotation, save for little whirlpools, quantum whirlpools. The quantum condensate, a new state of matter. To behold an image of this coldest conglomerate in the universe, we may turn off the invisible bowl, disperse the atoms, destroy the condensate, and in the act, capture its exquisite imprints on a camera. And then we may begin the magic all over again.
Moving.
Gliding.
Bruising.
Sliding.
Common conglomerate.
Common dance.
Flowing superfluid.
Unified quantum being.
Alas, coming down isn't pleasant. Or should I say, surfacing up.
What's happening? Reality just did. Ow! Brace yourself. The terrain here is horrifically rugged.
Where is here?
We're inside a raw material.
Oh, what?
Inside a solid. Inside a hunk of metal deep, deep down within its quantum recesses. Oh, my vision's getting blurry. What can I say? You're in a crystal lattice.
What?
A crystal lattice. And there's disorder, dissipation. Just keep walking. We need to navigate our way from one end to the other. I feel hot.
I'm being bombarded.
It's the electrons. They're everywhere, trying to get to the other end, just like us. Like us? Yes, they're hot too. They might get stuck in here, just like us.
What?
Huh?
Stuck? Oh, help! Help!
Oh, there's liquid everywhere! Hurry! Get to the plug! We're surrounded by the Fermi Sea! The what? The electrons! They formed a treacherous Fermi Sea!
A sea? Oh, but I can't swim! Oh, I just want to take a walk in the woods and then you show up! And now I'm gonna die! Oh, I'm gonna die in this Fermi Sea! Oh, no!
Get to the plug! Gosh!
I just want
Gosh! Gosh! Get to the plug!
Relax. All the same electrons. navigating their parent crystal lattice through the order, through the disorder. Relax. Relax.
Did you say a Fermi Sea?
Yes, we're surrounded by it.
We're inside the crystal.
Aluminum, perhaps?
Lead.
Aluminum.
Lead.
Aluminum!
Relax!
Well, whatever it is, it's a lattice of atoms.
Positively charged atoms. Arranged here and here and here and here.
And the electrons have formed this nebulous continuum, sweeping their way through.
By encountering impurities, defects.
And yet, somehow navigating their way through. But how does the Fermi Sea figure into all of this?
Oh, somebody help! Monica!
In metals, electrons are not confined to nuclei, but are instead free to move about the material, forming a Fermi sea. However, electrons are unfriendly creatures, called fermions, who refuse to all pile into the same state with the same energy. If we add electrons to build the sea one at a time, each would prefer to occupy a different energy state. The laziest electrons, which sit on the very lowest rung of the energy ladder, move the slowest. Each additional particle will occupy the next rung of the ladder, one quantum of energy away, each moving a little faster than the previous. Metals have a huge number of electrons, on the order of 10 to the 23, so the last few electrons will have an extremely high energy and move around the fastest. And it is these electrons that mainly account for conduction in the materials. In a perfect world, the most energetic electrons would dash across the material in an organized fashion, like athletes sprinting on a track. But real materials are filled with defects, like on a rough, bumpy road. Electrons scatter off of these imperfections, a process that dissipates energy in the form of heat. This sounds complicated and chaotic. However, physicists can exert exquisite control over the way electrons behave, like a choreographer directing a group of dancers. Applying a magnetic field causes the electrons to start dancing in circular orbits. They waltz along the edge of a material in orbit-like trajectories, forming a one-way stream of current similar to traffic flow on a highway. Remarkably, these edge currents are impervious to scattering because they can't easily change directions and therefore transmit electricity exceptionally well. Alternatively, experimentalists can engineer the energy of electrons to be very small, even smaller than the Coulomb repulsions between particles. In this scenario, electrons start exhibiting many-body cooperative behavior, like a group of synchronized dancers all spinning in the same direction. Nevertheless, fermions will be fermions, and the electrons all do this while avoiding and repelling each other. Finally, on a more practical level, electric fields can be used to turn on and off the flow of electrons, a feature that forms the basis of modern computing.
Well, all being fermions stacking themselves one upon the other, together forming this Fermi Sea.
The tumultuous, dangerous Fermi Sea that nearly put an end to us.
This is all your fault.
My fault?
Well, yeah, the photons, the superpositions, the smearing out in equal parts.
It's fascinating. If you don't see that, then I don't know.
But then you go off and do the Bose-Einstein dance, and then all hell breaks loose.
Yeah, that was great.
But then we nearly drowned.
Yeah, not so great.
And then you slapped me?
I saved your life. You're welcome.
Oh, okay, well, here we are trying to discover the nature of reality, and you're doing it all wrong. You think you could go off on these flights of fancy and cruise along with condensates.
And you, dear sir, think that discovery involves taking micro step after micro step, tearing things apart, fragmenting the whole? You can never understand the whole through its fragments.
Oh, well, you think that you can just discover reality in your bones, and you think that the song and dance that you do make up your delusional reality.
Well, you can't understand the whole through your nosy, systematic, analytic, excruciatingly dissectional methodology.
You have no method, just madness.
You have no madness, just method.
Oh, you'll spin everything into anything that just suits your...
You'll spin anything into everything that suits.
Oh, I cannot take this journey with you.
I cannot take this journey with you. It's finito. Done, done, done. Ah! I'd rather go alone. Stop! Sapienza, I need another Planck.
We are Planck quanta apart.
Oh, the world of fermions! I should have known. We're all fundamentally fermions. We can never coexist in the same state. Why did I bring them on this journey? There's no holding them together. So, is that all? Does it all end here? Is there nothing I can do to bring fermions together? Nothing to be done?
Back to our action-packed story in just a moment. But first, were you ever a child? Were there other children in your family? Did you ever experience what professional child psychologists call sibling rivalry? Did you ever incessantly flush the toilet when they were taking a shower? Did you ever precariously balance an open bag of flour on the upper ledge of their door so it would fall on them and make a tremendous mess when they'd enter their room? But enough about me. Look, whether we admit to these things or not, and being a quantum sage, I know who among you is guilty, it's quite common that siblings may experience what in professional psychological parlance are called issues with each other. They often try to avoid each other. Nevertheless, you can usually find them together around the table at dinner time. And why is this? It is because the strong positive attraction of a good home-cooked meal and the coercive powers of parents can overwhelm their natural mutual antipathy. Electrons in solids are like children in a very large, weird family. They're little brats running around all the time, trying to avoid each other because of their common negative charge. Like charges repel. They were each birthed by a neutral atom, which in parenthood became a positively charged ion. The ions attract the electrons, and on average, the system is neutral everywhere. But when one of the ions is displaced, local charge neutrality is temporarily violated, and there is a surplus of positive charge in the vicinity of the displaced ion. Like parents, the ions are big and slow and can only move around a little bit. But the electrons react to the displaced positive charge like kids respond to the dinner bell. In physics language, the slowly evolving ionic displacements, called phonons, are said to mediate an effective attractive interaction between the electrons. Now go give your sister a hug. We may push this analogy even further. In some families, parents may sit down for dinner and be joined by one of their children while another kid turns up somewhat later, after the first one is back up in their room wasting time on social media and the parents are away from the table watching Netflix or reading a book. Thus, the children show up in the same place, but not exactly at the same time. In physics language, this is what is called a time-retarded or delayed attractive interaction. Electrons in superconductors behave the same way. This delayed effective attraction further helps the electrons to overcome their natural instantaneous repulsion. The physics is, of course, quite a bit more complicated and involves quantum mechanics, Paul's exclusion principle, and a fair amount of mathematics. But the end result is that the effective attraction between electrons results in a state in which the electrons are paired. This special pairing state is what we call a superconductor. Superconductors exhibit an array of remarkable properties, including vanishing electrical resistance below a critical temperature, expulsion of magnetic fields, persistent electrical currents which flow without dissipation, and fascinating behavior at a junction between two superconductors known as the Josephson effect. The theory of superconductivity was developed by John Bardeen, Leon Cooper, and J. Robert Schrieffer in 1957. At the time, Bardeen was a professor at the University of Illinois at Urbana-Champaign. Cooper was his postdoc and Schrieffer his PhD student. Their work forever changed physics and was one of the great triumphs of 20th century science.
And thus, perhaps no two fermions can be in the same quantum state. But then again, my crumb snatchers, you aren't in the same quantum states. Two fermions of opposite spins come together and pair. Two fermions of different orbital momenta come together and pair. Two fermions of entirely different dispositions come together and pair. Two fermions, one having flights of fancy, the other endowed with systematic methodology. Only in pairing can they enter new terrain. You can't go it alone.
Lo, they can be bound from afar, as electrons are within crystals, sensing the other's presence, roaming in resonance.
And why just one pair? Plentiful pairs could there be, as pairs no longer unfriendly, ready now to condense to form that communal quantum state.
Superconductivity!
What becomes now of the Voyagers? Come they together to overcome strife, to find harmony?
Alas, fellow sojourners, these are uncertain times, and the constraints of time and space imposed upon us on the Zoom world compel our voyage to take a pause.
We have seen glimmers from many a realm. There exists a soft glow endowed by the quantum world within each one of us. And it shall lead us through the shadows into effulgent light.
So, Aditya? Aditya? Aditya, can you hear me?
I think Gobi Aditya is
Yeah,
facing
hi.
some internet. Oh, he's back. Okay.
No. So I have not the, yeah, now I'm the co-host, so I can unmute myself and start my video. Hi. So I hope all of you enjoyed who were present for the screening of the play or the virtual version of the play, enjoyed it a lot. I see that a few people have joined us at 10 o'clock and on YouTube as well as Zoom. So I'll just inform you that what we just finished was a screening of the virtual version of Quantum Voyages, the play by Professor Smita Vishweshwara, who's kindly agreed to be with us today. So before we go ahead with a kind of conversation about different aspects of the play, both scientific, artistic, about theater, and what are the challenges of making it into Zoom and YouTube, etc. I would just like to introduce Professor Smita again for people who joined late. So Professor Smita Vishweshwara is a professor of physics at the University of Illinois at Urbana-Champaign. She maintains very close ties to scientific, educational, and cultural establishments in Bangalore, which we will be talking about quite a bit. On the research side, her research explores the coldest states of matter in the universe, nanomaterials, strange quantum particles, black holes, proteins, and more, and some of which you will hear about today as we go forward with the conversation. She's a fellow of the American Physical Society, a Simons Fellow, and an inaugural Margaret Burbidge Visiting Professor at UCSD, where she's currently joining us from. Over the past several years, she's been combining her passions for both the arts and the sciences. In particular, she's developed an interdisciplinary project-based course where the arts meets physics at UIUC, which students conceive, build, and share their marvelous creations from the quantum to the cosmic. She has also collaborated with theater makers, as you saw in the screening today, dancers, musicians, visual artists, and more to create several works, including a performance adventure tale that you just saw called Quantum Voyages, and a meditative visual music narrative piece called Quantum Rhapsodies. So without any further ado, let's just get to the conversation, and welcome, Smita.
Thank you so much, Aditya, and thank you all for joining us and for ICTS for having this beautiful festival and for inviting me to be a part of it. It's always a joy to be with you all.
The pleasure is all ours. So let's just start with about your background. So I understand that you grew up in Bangalore, and as I also introduced you, you also spend time doing a lot of things at the intersection between science and art. So where do these overlap of the interests and an interest in art while also being a scientist come from?
So maybe I should, as you said, start nearly at the beginning. And I don't mean of the universe, but that's a fine place for art and science and everything to come together. No, of my life after being born in Pittsburgh, almost immediately, you're right, my parents moved back to Bengaluru. And I think right from that very early stage, so not only do I have all these cultural and scientific and artistic and educational ties, I have very, very close familial ties as well with my whole extended family. So maybe I can just, show you a little bit of what life was like and how it evolved. So let me just try this modern Zoom way. And let's see, can you see my screen? And then I'm just going to do the slideshow here. Yes. So can you see my slides, Aditya?
Yes, I can see your slides.
Yes. So there it is. This is my biophysicist mother and myself and my sister Namita when we were little kids. And we were always, and this photo is taken by my father, C.V. Vishweshwara. And so we've always been a very close-knit family. And my father was a black hole physicist. So, we were surrounded by science, but we were also surrounded by arts. In fact, one of my grandfathers, C.K. Venkatramaya, was a playwright. So I grew up in that whole kind of theater. Our uncle, C.V. Nagraj, violinist, lived with us. So we were surrounded with Carnatic music all the time. And we just grew up steeped in this environment. And what you see here, for example, is from the Valley School. And both my sister and I went there, and now I have a nephew there, in fact. So that was where we would not only explore the usual curriculum, but J. Krishnamurti, he had this whole alternative education where we really were taught to explore arts. That was a big part of it. And that arc sort of followed me throughout my life. What you see here is a sort of protein network structure that my mother studies. I'm a condensed matter physicist by training. I also got very interested with my mother's work, and so we collaborate as well. And if you look, always sort of the arts and the sciences came together. So for example, I'll show you work here by one of her former students who also is a beautiful artist. So this, I believe, is his artwork on cancer cells. So it's part of the tradition. And one person who's played a huge role in my life in sort of bringing together the arts and sciences as just a way of life, my late father, C.V. Vishweshwara, he was a black hole physicist, and recently you may have seen in the news, he's referred to as the black holy man of India. He discovered some pretty fundamental sort of theoretical predictions on the way black holes whisper to you, quasi-normal modes that they're called, among many things. But he was also the founder director of the Jawaharlal Nehru Planetarium in Bangalore. So you can see so the way he worked was really sort of working with artists all the time. He would script his own shows and then work with visual artists, musicians, and a wonderful, wonderful team at the planetarium, which is sort of almost like adopted family for us. And they would just bring it alive. He also wrote books, cartooning. And so I think this is very much entrenched in me. And so there's that sort of whole outlook, which is just ingrained. So it's all an organic part and parcel. So very briefly to tell you what I do. So after doing my high school in India, I went to Cornell as an undergraduate, and I was a physics major, but I lived in an artist's dorm. So, it was physicist by day and indulging in artistic pursuit in the evenings. And then Santa Barbara, as a graduate student, I went into condensed matter physics, which, as you said, looks at some of the most fascinating quantum states of matter, the coldest states where you see quantum physics, this very strange, mysterious, spooky thing come alive. And so I started doing that as a graduate student, but I'd always have something else going on, writing, being in a choir, all kinds of other things in tandem. And so that's been my life throughout. Here you see capoeira, which is a Brazilian martial art. This is a choir, all things that that I've done through my life. And I think a moment came when I became faculty, and several years into it, I thought, I should just bring these two passions together and make it a part of, a way of life. And so here I am. And I hope that answers some of it. And actually, since we're having a conversation, Aditya, a question for you. I believe you too have this sort of inclination.
Right.
Can you say a word about your experience?
Right. So I like to, I think this slide summarizes it extremely well. I look at my research career as an 8 to 6 thing that I do in the morning till the evening, and 6 to 9 in the evening. So a couple of hours go into, so I do theater on the side. with an amateur theater group here called Stagecraft, which is based out of NCPS. We are a group of people who are all PhD students or postdocs, and we perform in Bangalore quite often. Of course, we've not done it for the past year because of the pandemic. But yeah, I mean, I really find it interesting because I see that it also feeds back into my science, because there is you always need to look at things from a different perspective, and you need to refresh your mind to come back the next day and start working on the same problem that you've been working for 1 year, 2 years, whatever. And so this really helps, not just as a hobby, but also as something to get this different perspective from.
Absolutely agreed. And I think one thing feeds off the other too,
yeah,
including formation of ideas, I think.
Correct. We'll actually talk about this a bit later in our conversation, but now I want to come to the play itself. So the play, as we saw, I mean, if the YouTube version is anything to go by, and I hope if pandemic was not there, I hope I could have seen the play live somewhere. But if the YouTube version of the play or the virtual version of the play is anything to go by, this looks like a very dramatic piece with a lot of movement, with a lot of very dramatic pieces all coming together to explain quantum physics and stuff like that. In that sense, it's a pretty unique idea. So where did this all start? What was the conception?
Okay. Should I tell you about the conception and also sort of the whole process, perhaps?
Sure. Please go ahead.
Okay. So I think so let's go to Quantum Voyages, and the person that I created this with is Latrell Bright, who you see here. She's a phenomenal theater maker. She devises work, which means create new pieces. She does acting, she does directing, and everything from very intimate, gripping theater to sort of large scale productions. So how it came out to be was the following. 2016, and this was when you all had worked together, and there was this landmark detection of gravitational waves. There was all that excitement, and one of the dreams of my father, in fact, to see it, and he actually did do that. And then I think shortly thereafter, what happened was these ideas had been brewing, and the course that you mentioned, I just started offering that. And at that point, something, slowly this idea came to be of why not depict both the cosmos and the quantum world, these two worlds that I really deeply love. Why not depict it as an opera piece, something of operatic proportions? And I think one thing I should also say is when you watch the piece, as you say, when you watch it live, it's a very, very different experience. And what I thought was that if you look at ballet, opera, and just dance dramas, Bharatnatyam, for example, take any of these very rich cultural things, oftentimes you see a voyage and you see them going through these different lands. And, take, for example, Bharatnatyam, I mean, a lot of these songs could be in Tamil or Telugu or, some Sanskrit languages that we may not know all the intricacies, you may not know everything there, but you can follow the journey and you can see that there are these adventurers. So this, I thought, why not do the same thing with the quantum realm? It's mysterious. It's the world we live in. And maybe we can open this up as a sort of journey where we take the audience, where they don't have to understand everything. We don't understand it in spite of spending 20 years, at the deepest level. So maybe just go through all these beautiful phenomena that we study through this adventure journey. So here you see the two main adventurers, Terra and Akash. So this idea sort of came in my head, and it happened to be, I proposed it to the Krannert Center for the Performing Arts, which is a marvelous place in Urbana-Champaign. And it was just sort of this very naive dream. Yes, let's create this, opera. Naivete has taken me quite far, I'll tell you. So I just go without even realizing how, if I knew before, I'd probably would just not do any of this. But it was a very beautiful moment when I was wandering around with this idea in mind. And there was Samuel Smith. He's sort of the Krannert Art Center. He's the director of civic engagement. He's really a hub. And he said, "Oh, Smita, come here. I want to introduce you to someone." And it was this beautiful, marvelous person walking from the other side, Latrell Bright. And somehow we immediately clicked. And, I told her this idea. It was just a nebulous idea. And she said, "Let's do it. Let's do it." And so it really was a collaboration with all these elements, imagining and researching. So and I, of course, my sister, she's very involved in theater, and I told you about my family history, but I myself didn't actually ever script a play or anything. And of course, that's what Latrell does. So we started working together. It was absolutely beautiful. So for a semester, we scripted. And then the next part was to workshop. So we would bring a small group of people together. And like you said, there's a lot of motion and dynamism. So we really had to have physical bodies bonding together, just connecting. And Latrell has amazing exercises for that. Aditya, you probably do these as well as in your theater experience.
Right.
And yes, and so a lot of the devising also happened once we saw them and what motion was possible and not. And then the thing with the sages, the quantum sages, I really wanted to bring in physicists and all their diverse voices and, the very rich kind of ideas that they come. So they would come in moments of strife. And we'll talk about the Fermi Sea where these voyagers are drowning. So they invoke the sage, and the sage comes, imparts wisdom, and saves the day. So that was kind of the idea. And the physicists themselves brought a whole new element. And it was so marvelous the way Latrell works with them, works with people. She can just connect. So every time we have a production, it's a new set of physicists. So like you said, when we bring this to Bangalore, which will happen after the pandemic, we will have local physicists, So so you can see all these aspects. This is Latrell and me at work at the stages where we had to script, and we do visits. So for example, there's an MRI scene which you didn't see in this one. We'll explain why that's true. But we went to the Beckman Institute where we saw a functioning MRI. So we do that kind of research. Here you see these sessions, these rehearsals. I'd go to every single rehearsal, and Latrell would have me very involved in the whole process of rehearsing, because the scientific accuracy is important, even if it's just, even if the audience doesn't necessarily know that that's true, they have to feel it in their bones, as Terra would say. And so we'd have so much fun just going through that whole process. And finally, this whole piece came together. And maybe I'll put up the slides, slide right here. Also, so that's my answer. And one last thing, I don't know if we should be monitoring the chat box. I'll let that in your hands.
Yeah.
So anyway, that's the story. That's the story of how the piece came to be.
Yeah, I found it really interesting that you drew parallels to, Bharatanatyam performances where it is storytelling, right? And in some sense, I mean, though we call it a dance form, it is forms like Kathakali, Bharatanatyam, all these are storytelling art forms. And also the fact about, different languages. So I was also sort of amused by the choice of names for the characters. Terra, Akash, and Sapienza. I mean, I guess they're three different languages. So why did that happen? Is there a reason behind that?
Yes, just where we have some sort of affinity to each of them, and you're absolutely right. We wanted something from the different cultures, but also something, that's authentic and true to our roots. And so ours now in particular, where we're having this at the ICTS. So Sapienza, actually, if you, there's in Rome, one of the universities is called La Sapienza. And somehow, to be honest, another thing that happened, and we'll talk about this later, when I first had this idea and I had this proposal, where did that go? Oh, okay, here, yeah. You can't really see it here, but I had this conception that it's some Grecian or Roman kind of thing, here, you see it here. And the way Lattrell, and also I was teaching this course, so a lot of the people in the course also got involved. They completely changed my worldview. It's like, just maybe you can have something modern. For example, Sapienza here, who you'll see, or we can go back here. Where is she? Anyway, I don't know where she is. She's here. We'll talk about her. This Sapienza here, she's very modern, and it's actually even the costuming is very carefully thought through. So in fact, she's sort of has Amelia Earhart. So this was, quantum physics came in the early 1900s. And so Amelia Earhart, she was a pioneer. She was a pilot, she did these, she was one of the first to do all these flights. And so it just seemed appropriate. Let's not have an ancient Greek. I mean, quantum physics is modern. Let's come up with a more modern thing. But we still kept sort of that Roman, La Sapienza. Akash, I just, there had to be something Sanskrit, and Terra is, of course, the ground. I also have a dear friend called Teresita. So she's, so it just, Terra just seemed, and Earth Day is coming up soon, but the Earth is something so precious. So that was something. Interestingly, we switched the nature of these two characters. So Akash is the one who's very grounded, and Terra is just up in the sky and visionary and things like that. So yeah, but the names definitely have sort of a history behind them.
Right. Yeah. I mean, that did come across in the play as well. The fact that you switched the names and this picture especially is very interesting. And I mean, when I saw this picture for the first time of of Sapienza in this modern costume, that's exactly what my thought went out to. Because if this was a Shakespearean-like play, this would have been the Shakespearean-like costume. But whereas this is a pretty modern way of doing things, which is really interesting.
Right. Yeah. And I should say that actually the other thing that's very interesting is I think both Lattrell and I have this way where we just see the people in the room, so to speak, and see what talents they have to offer, and then we incorporate it. So it's a beautiful process where you just sort of suspend holding on to my idea, and that's what it's devised work, and it's communal. It's like the bosons that you saw, it's very communal. So for example, in this particular one, Cassie, she was taking my class, and she was a very, very serious physicist, and at the same time undergraduate in her last year. She said, I took this course and I just want to be involved in quantum voyages. Somehow they came for rehearsal. We said, okay, what are you interested in? And she said, fashion design. And we said, okay, let's then you figure a way of bringing this in. Why don't you design the costume? The analysis that went into her thing was remarkable. She went back, she looked at what was the whole setup like in the 1900s. There was also this idea of steampunk, which is yet another thing which borrows from the Industrial Revolution. So you can see gears that are attached. At first we thought, shall we go with that style? But when she converged on this pilot costume, so to speak, it made so much sense. Sapienza, she's the spirit of wisdom. She can fly anywhere, right? And she can be present at any place. And this is why we bring in the sages too. If you're the spirit of wisdom flying around everywhere, then you can't get to the edge of knowledge. You have to have some help, which is why the sages also come in. But yeah, so a lot has gone into this.
Yeah, that's a very interesting perspective of looking at the whole concept of sages and the path. I mean, people who show you the path, stuff like that. Right.
And,
so, yeah, please go ahead.
Oh, no. And you can also see that the Indian elements are quite evident, right? So, for example, in the virtual version, so the sage itself, and of course, everything, when you bring it to the modern perspective, when you bring it to the global perspective, the meaning morphs, and we like that fluidity. But also the Tanpura, for those of you who've just joined us, if you go back and look at the thing on YouTube, you'll see that we use that quite a bit as well. So
right, yeah. I mean, the Indianness is there, right there in the production. Okay, so now I want to discuss the most scientific aspects of the piece. So, in fact, can you please stop your screen share so that I can show the audience a small clip from the
Absolutely. And before I do that, maybe I'll quickly just say that the reason I have all these is we start off with light, then it gets into this very, very tricky scene of what is the meaning behind quantum physics. And then we have the coldest states of matter. And then there's this, what's called the Fermi sea, and then superconductivity, and finally MRI, which we didn't do in the virtual version. So those were all the scenes that were there. And let me stop sharing now.
Yeah, thank you. So I'll just share my screen and show everybody a short clip from the YouTube version of the play. And so here it goes. So this is about the Fermi sea, and I won't really spend a lot of time talking about it, but here's this.
What's happening? Reality just hit. Ow! Brace yourself. The terrain here is horrifically rugged.
Where is here?
We're inside a raw material.
Oh, what?
Inside a solid. Inside a hunk of metal, deep, deep down within its quantum recesses. Oh, my vision's getting blurry. What can I say? You're in a crystal lattice.
A what?
A crystal lattice. And there's disorder, dissipation. Just keep walking. We need to navigate our way from one end to the other. I feel hot.
I'm being bombarded.
It's the electrons. They're everywhere, trying to get to the other end, just like us. Like us? Yes, they're hot too. They might get stuck in here, just like us.
What? Stuck? Oh, help! Help!
Oh, there's liquid everywhere! Fermi sea! The what? The electrons! They formed a treacherous Fermi sea!
The sea? Oh, but I can't swim! Oh, man, I just want to take a walk in the woods and then you show up. And now I'm gonna die. Oh, I'm gonna die in this Fermi sea. Oh.
Get to the plank! Akash!
I just want
Akash! Akash! Get to the plank!
Relax.
Right. So that's a really dramatic scene. I mean, I can only imagine how this would have played out in a real theater with, 500 people sitting in the audience or whatever. So, I mean, so it does two things, right? So it does also create a sense of anxiety, of drama, etc., among the audience, but it is also trying to explain a very intricate scientific concept. So, first of all, would you like to talk a bit about the science that went into this?
Sure, yes, definitely. The point, and there's also, I see a few questions in the chat box. I'll answer those as well. Actually, let me just answer those, and then I'll definitely get to the physics, because it's related to Aditya, one of your previous comments. It is indeed a very dramatic scene. Someone comments on the slap. It's because Akash can't swim and he's just going crazy, and Terra has to somehow rouse him out of his sort of panic, because that's the whole thing, right? If you're swimming and you can't swim, you panic, it's worse. And then the get to the Planck is supposed to be a pun, because Planck is one of the founders of quantum physics. So, but the Planck, right? Yeah, so yeah, so that was supposed to be a pun, which is much more evident in sort of the real setting. As for the slap, so Terra kind of slaps him and jolts him, so he actually gets into action. But in the sort of physical one, and I showed you photographs of that Terra and Akash, and Gloria Lee played Terra there, and lovely spirit. And Akash is also Michael Hyman, another very lovely spirit. And it was so hard for her to fake that slap, so because she's such a nice person.
I can relate to that.
So Latrell was egging her on, get mad, just think, and she couldn't. So, but later when she did it, it was just really dramatic. But coming to the physics, what's going on inside metals is even more dramatic. And so, for example, here I have my mother, it's her wedding bangle, in fact, gold. And if you look, it's just gold, aluminum, nickel, take anything, any of these. What's going on is, why do they conduct so well? It's because electrons can move around, but really what you have is this lattice of these positive cores, of atoms, and the electrons, there are few electrons, conduction electrons, that can hop from core to core. And so the idea here is, these are called fermions. These are elementary particles that hate each other, in the sense of, if there's one fermion here, there cannot be another one here. So they just can't be in the same state. So as a result, what happens is that they start filling up different energies. And so if you look at the fastest moving electrons, this is going on in the metal around you, they're moving about the 100th the speed of light. The only thing is, if you look at the crystal, and maybe I should share my screen, because I'll show you. So, and this in fact is a lovely painting that one of the Danielle Markovich, she made, and we use that as a stage set as well. She did this painting here, and you can see actually, this crystal lattice. And somebody mentioned dislocations. So those are now on the right top, that is a real crystal. Actually, it's an image. So the electrons are moving around, they're bouncing from place to place. And that's really what's going on inside. And so we wanted to recreate that. And this down here is a photograph from the live performance, so you can see sort of how dramatic that was. So yes, sorry, there's one more question from Ajit about getting these senior physicists. How do we actually get them onto stage? Remarkably easy. Physicists, though I say so myself, are pretty amazing. not only in the work that they do, but also just how social, how smacking they are in character, and how expressive they can be. And we had so many different kinds, everything from Gina Lorenz here, who wrote a whole iambic pentameter thing on light, to Brian DeMarco talking about the coldest states of matter in this beautiful way. And then later I'll show you Tony Leggett as well. So that's just a side comment. But I hope I answered your question on the physics behind this.
Yes, pretty much. And it's really interesting for me to see, as a person who always is trying to question how I can communicate my science to the public. This is a brilliant way to do that. And I would really look forward to actually watching this on stage if it ever comes to Bangalore. That is.
Thank you. We should just make it happen. But also, all of you, there's so many of you who are so multi-talented, and I just encourage, these kind of pieces can be made too. So maybe there can be new work devised even, but yes, we'd love to bring this your way.
Sure. Now I would like to show one more clip from the piece. And this is actually about a real, in physics circles, it's probably a more contentious issue about the interpretations of quantum mechanics and some such, but, and it's of course very, interesting to the public eye as well. So I'll just share my screen again and just play this clip. So this is from the middle of the play, most probably, and here it goes.
Miss Scarlet in the study with a wrench.
Mrs. Peacock in the cellar with a revolver.
Mr. Green in the hall with a knife.
Colonel Mustard in the dining room with the lead pipe.
All possibilities are mixed or smeared out in equal parts.
Like in a game of musical chairs. Reality comes into being only when the game is observed and the music stops.
Ladies and gentlemen, I have followed a string of observations and concluded beyond a reasonable doubt that it is indeed Colonel Mustard who performed the heinous act in the dining room with a lead pipe.
So it's at this point that all the morbid possibilities, mixed or smeared out in equal parts, that we collapse onto Professor Plum being the true killer.
I beg to differ. I would like to think the killer existed all long before Detective Irwin's observations.
Oh, my little crumb snatchers. Reality, it could be way worse. All possibilities could be smeared out in equal parts, and that is the reality.
No way.
Yes way.
And so we begin again.
Oh, you're on mute.
Sorry, I tend to do that a lot. So this is like one of the episodes from a 3-episode sort of game that you've conceptualized as to explain how people interpret quantum mechanics and how it is different from classical mechanics that we tend to observe all around us or we are familiar with. So we want to talk a bit more about why you put it in this way, and also about the science, of course.
Yes, for sure. And again, it may be useful to show you some things. So first off, this was the hardest scene to stage and everything, everything. Conceptualize and sort of bring to life in terms of theater, but also in terms of the science. And but this is something that's so fundamental to quantum physics. In the formative years, when this started off, there were so many philosophical debates in the early 1900s. And what's the nature of reality? So it was really, and back then, science, philosophy, all this, they were all much more closely integrated, including the practitioners. So there was Niels Bohr and Heisenberg and others, they belonged to this Copenhagen school, it was called. And they came up with this, all interpretations are crazy, but this crazy interpretation that something can be in the superposition of many states, and be is a loaded word. What does it mean to be? Very Shakespearean. So we actually put that into to be and not to be is what we say. So, but this is more like an electron can be here and here and here and here and here. And according to them, it's in that superposition of many different things until you make an observation, and then you can only see one. And Schrödinger, who you see here, and Einstein, they all just were kind of, it made their skin, it's kind of just crawling under their skin. And Einstein is supposed to have said, I'd like to believe that the moon is there even when I don't look at it. So it shouldn't be the act of observation that determines your reality. Schrödinger, that was when he came up, we won't go through this, but this thing that you see on the right below, it's one can't write papers like this anymore, unfortunately. It's very beautifully written, sardonic, one can even set up quite ridiculous cases. A cat is penned up in a steel chamber along with the following diabolical device, which must be secured against direct interference by the cat. This beautiful dramatic thing he writes, and he finally comes up with a scenario where if you believe this interpretation, you can come up with a situation where a cat is dead and alive in a box, until you make an observation. So all possibilities are likely until you make an observation. I was explaining this to Luttrell, and then, in one of those sessions we had, and I still remember going in to get some, this was in my house, and in the kitchen, we were just heating up some tea and chatting about this. And then she said, oh, you mean it's like that game of Clue where the murderer, who the murderer is, it's a murder mystery game, the name is put in the envelope and you don't know what's inside the envelope until you see, until you look in and see what's inside. But the question is it that any name can be there? They all exist at once. And then when you pull it out is only when it becomes that? Or was it one name all along? Which one is it? Or are there parallel universes where there's a different murderer in each situation? And we thought, oh, this is such a sort of fun way of denoting all this, right? So that's why we came up with this quantum clue game, and we could give all the different quantum physics interpretations through this game. And of course, it's so hard to understand. They have to go and invoke a new sage. So you can see as here, this is the devised work down here where we're in the studio trying to come up with because the language is very precise, and so we're rehearsing, getting all the positions right. We do it as a musical chairs as to who is the killer, whoever's out, that we did a musical chair thing in the party. So there's a party and this is where the murder happens. So we just thought it was fun. And then at the end, finally, you have to invoke a sage to really explain this. So this was our our premier event, which was this is Tony Leggett. He's my mentor. He was my postdoc mentor. He's my colleague now. He also Nobel laureate for understanding superfluid helium properties, and he's a knight too, knighted by the Queen. But and as Ajit's question, he just so nicely came onto stage, did his explanation. You see we call them the quantum ensemble. They're sitting there listening to Tony. Yeah, so that's how that scene came to be. And this on the right is Tara inside that crystal in that Fermi scene. So.
Right. So this is, I mean, this picture, I mean, I'm also seeing this for the first time, the one with Tony Leggett in it. And it's somehow, goosebump inducing as well when he's explaining things that he's worked on and tried to understand for so many years in a science communication way as well.
Absolutely. No, it's extraordinary. And this is the thing about Tony. He just deeply thinks of anything. So when he goes up there, he was very authentically and sincerely explaining to these quantum ensemble that have just, lounged on the floor, telling them the secrets of quantum physics.
Right. Yeah. And I really like this as a form of, reaching out to people because people, I have friends who, when I start explaining these kind of things, just say, shut up, you don't talk about it. But this, I guess, when one puts it in such an artistic and dramatic, interpretation of it, it just becomes so much more lively and it becomes so much more interesting. I mean, kudos to that.
That was our hope. And and also, this science is considered sort of esoteric, but if you look at it, what I do, quantum many body physics, so to speak, sort of the rules, we can humanize it, understand it in an anthropic sort of way, and then you can see a lot of these things that are around you. The quantum world, it's the building blocks of who we are, let alone these strange states of matter. And I really think when you cast it in this form, not only can the public understand, grasp some of it, they give us insights like, oh, why couldn't this person have run this in this way, And then you think, oh, wait a minute, can electrons behave like that in crystals? So it's actually, there's a nice cycle there.
Right. So I think we are nearing the end of our time. So I would just like to ask you one thing. So of course, a stage play is meant for, 500 people sitting on 500 seats, and there's being a elevated stage and people performing on it. What was the thought process behind, adapting it for YouTube? I mean, I can understand probably was a necessity given the times, but what was the thought process behind it, and how did you go about it?
Oh, yes, it was all very dramatic. So, we had some of these live performances, and then the plan was, as you mentioned, I was on sabbatical at UC San Diego in starting 2019. And as you said, thanks to the pandemic, I'm still in San Diego, now back to University of Illinois, running, so to speak, the San Diego branch, perhaps. But, and this was as part of this Margaret Burbidge visiting position, an extraordinary astrophysicist, 100 years old and she actually passed at 100 last year, in fact. And it was such a privilege to sort of, go there in her name as a visiting faculty. And part of, in addition to research and collaborating, in fact, including with two of the sages that you see in this production, Dan Arovas and Yizhuang Yu, the idea was also to bring this to San Diego and to Santa Barbara, my alma mater. And that's when, so then what happened was it was February, and this I'm putting this here because there was in February 2020, I gave this talk in San Diego. We were meeting in person. We were going to get everybody together. And then this is when sort of the pandemic happened. And by the way, my mother and I we're working on the spike protein, sort of that evolved. Also learning music from the same teacher. And in fact, there's the Tanpura Droid app. that's what we use for our production as well. But this was when it hit in, well, for us, everything shut down in March last year. And this is when we just about started to do auditions. And the idea was Latrell would bring some of the people from Illinois, and then there'd be a local group also in San Diego. And everybody said, we're going to stick with it. We're going to make this happen. And, you know, for all of us, this period has been so challenging. And to have these people come together and say, for these times, we just have to do it. We have to have this to offer. And we never met in person. We still haven't, except Levani here. I met him in San Diego, and you know, he's in theater. So we'd met, and of course I've met the Urbana people before, not all, in fact, not one of the protagonists. So, and the whole Quantum Ensemble, we'd never met in person. And so then we did it all on Zoom, and our big savior here that you see with the Van Gogh painting, Nick Morse, the videographer who we work with a lot, an amazing artist, he came on board and we said, we're going to do the whole thing through Zoom. And so we had 2 months to get this all in order. And we told the UC San Diego people, we will perform. Week after week, are we going to come? Are we not? Are we going to have partial live? Is it all virtual? And at the end, it all became virtual. And we couldn't do the last scene, but we said, whatever we can do, let's just offer it. And so that's how we have this production.
Right, and thank you for it, so that, you know, I mean, a lot of us could see it without actually being present in the USA, and that's really a nice thing. Right, so to end it all, I would just like to ask you what you thought about, you know, the overlap between science and art, and how, because people have this preconceived notion that the method of artists is very much different than the method of scientists, right? So what are your thoughts about it, and what's the future of Quantum Voyages and your other voyages into the intersection of art and science?
So I think everybody has a different outlook, but since we've run out of time, I'll just tell you very briefly. For me personally, there isn't that big of a separation, because I should say, if you look at the conception of an idea, let's say, and of course you can say science, a lot of it is maybe studying things that are there, that, like the material here, or the galaxies and black holes and things like that. But again, I feel like there's a lot of ideas, exploration, imagination. You need all that. And artists in different ways are also at least partially expressing or reflecting reality in some way, perhaps. But for me, the main thing is, I should tell you that, you know, because we've scripted, I'm in my work, we're always thinking of new ideas. That moment where there's that, oh yes moment, for me, it happens when now I'm walking on the beach or something like that. It's this sort of beautiful moment where something happens and this idea comes. Or a lot of it can also be collaborative. You're in a room, you're discussing, and then, and for both, it's happened, both with art and with physics and science. And then there's the sort of analysis part too, you know, and it's this, for example, the scripting, just carefully thinking it through and sort of this creating this thing also took some, it's the other part of the brain, if you want, where you just have this analysis and rather technical. And then finally, in both cases, at least for me, it's important to ask, okay, what's the story here, right? And you said we're storytellers, and Latrell says that a lot, that we're all storytellers in different ways. And I do feel that with science too, you know, you have to ask, what is the phenomenon here? What is the story? And for me, that's also important. So it's all very organic in my experience, and I think my collaborators are as well. Oh, the future. lots going on. We also have an art science festival in a few weeks, and I keep saying, okay, I'll take a break from collaboratively creating new pieces. It just doesn't happen. It's just now it's so compelling. And I think you do this too, by the way, Aditya. You're also involved in both science and theater in particular. So I imagine that you may have a similar outlook. Mute, you're on mute.
Yeah, I do have a very similar outlook. And I mean, I should confess that I didn't have the same outlook in college when I was doing my undergraduate studies. And the things have completely changed as I've become an active researcher the last 3 years in ICTS. And yes, I do not think, as you had mentioned earlier also, I think these boundaries between science and let's say the arts or the fine arts or philosophy are created by us as humans. And you know what, 400 years back, it used to be natural philosophy and modern philosophy, and perhaps it's time to rethink the boundaries of divisions and stuff like that.
Agreed. Yes.
Yeah. Right. So yeah, I mean, I hope we get to see this play sometime in Bangalore, maybe at ICTS itself. At some point in the future. And with that, I'd like to thank you a lot for taking out your time. I think we can take a few questions from the audience, maybe 5 minutes, if that's fine. Anupam? Hello?
Yes, please.
Yeah, hello. Yeah, sure, we can take, I've already posted the questions from YouTube, which you have already which have been answered by Professor Smita. If you want to read, visit them again, or yeah.
Right. So I think there are a few questions from this chat itself. So there's one question which asks, Arush Murali asks, do quasi-particles collectively follow quantum behaviors, or do behaviors average out to appear as a single particle?
So let quasi-particles actually. Let me just explain that to people. So in some sense, as with communities, let me give that societal analogy. If you put a whole collection of particles, or let's say humans even, a lot of times what you see as a collective whole is very different from the individual. So quasi-particles are sort of natural, let's say, things that emerge from the system. I should say that, you'll in this particular theater piece, we talk about two kinds of particles, the friendly bosons and the unfriendly fermions. Just to say, no, quasi-particles, they can have their own completely different guise, so to say, and that's actually part of my research. I'm studying yet another kind of particle called anion, which is somewhere in the middle. So it's neither too friendly nor completely unfriendly. And so, yeah, so there are times where sort of this emergent behavior itself is what prevails, and that makes for a very interesting situation. And thank you all for some really lovely comments here in the chat. Very much appreciated.
Yeah, thanks. So I think we have time to take 1 or 2 more questions. So if anybody has questions, yeah, I mean, Siddharth asked, were you associated with the Chitrakala Center of Bangalore?
Is that Chitrakala Parishad?
I think so.
Okay, then yes, then the answer is yes. And actually, we go there often and all the time, and I should say that once my sister even performed there. There was a wonderful production of Animal Farm, in fact, and had a lot of music. I mean, I know that Chitrakala is not just, it's arts of all kinds, but just to let you know, I have very fond memories from that. And yes, so absolutely. And, it's sort of driving distance to where my family lives and where I live when I go back, when I visit you all. So it's, and I should say Chitrakala and a lot of the sort of art scene in Bangalore really has had quite an influence, and it's something really wonderful to carry across the world, I'd say.
Yeah, that's right. Yeah, I don't see any more questions in the chat, so I guess we're also out of time. We've exceeded our time by 7 minutes. Wait, just one question. Yeah, I guess we can then end it here, since we already 7 minutes past the hour. Thank you, Smita, once again for taking out the time. I know it might be a bit late now in San Diego, but thanks for staying with us for so long. And yeah, thanks everybody for joining. As everybody knows, the Cosmic Zoom is a continuing exhibition. For example, tomorrow at 4 o'clock in the evening, there's a talk by Uma Ramakrishnan on tigers. So if you're interested in wildlife and how people use DNA to study large animals like tigers, you should please check out this event. You can find it on the ICTS site or even the Cosmic Zoom site, I'm assuming. Right. Thanks, Smita, once again.
Thank you so much, Aditya, and ICTS and everybody here.
Yeah. Thank you, everybody who took part in this.